The cross product, Level 1. In this video, we will define a new vector operation called the cross product, also known as the vector product, and sometimes referred to as the area product. In the previous videos, we defined two ways in which you can multiply vectors together. The first was scalar multiplication, which produces a vector, and the second was the dot product, which produces a scalar. The third way to multiply vectors is by multiplying one vector by a second vector as to produce a third vector. The first thing to keep in mind about these three separate ways of multiplying vectors is that scalar multiplication and the dot product are defined for vectors in R squared and R cubed. What makes the cross product different from the first two methods is that the cross product is defined only for vectors in R cubed and not R squared. This is extremely important to remember. I repeat, the cross product is defined for vectors in R cubed and not R squared. When working with the cross product, make sure you're using three-dimensional vectors. Alright, with that out of the way, let's take a look at the geometric definition of the cross product. The cross product is denoted with a classical multiplication symbol, and, as the alternative name for this operation suggests, the vector product is itself a vector. To define the cross product between vector A and vector B, we will start by drawing the two vectors with their tails located at the same point. With both vectors aligned at a common point, vector A and vector B will lie in a common plane. Remember, the cross product is defined for vectors in R cubed, so we are dealing with three-dimensional vectors at all times. We define the cross product to be a vector with a direction perpendicular or normal to this plane, which in turn is also perpendicular to both vector A and vector B. The magnitude of this third vector is equal to the product of the magnitudes of vector A and vector B times the sine of the angle theta between vector A and vector B. We measure the angle theta from vector A toward vector B and take the smaller of the two possible angles. Similar to the dot product, theta ranges from 0 to 180 degrees. With the cross product defined this way, the value of sine of theta will always be greater than or equal to 0. This way, the new vector will never have a negative magnitude. Recall that the magnitude of a vector is always a positive number, or 0. By using an angle between 0 and 180 degrees, along with sine of theta, we are able to generate magnitudes that are positive, or 0. With the cross product defined this way, vector A and vector B are going to be parallel when theta equals 0 degrees, and will be antiparallel when theta equals 180 degrees. In addition, the magnitude of the new vector will be equal to 0. So it turns out that the cross product of two non-zero parallel or antiparallel vectors is always equal to the 0 vector. In particular, the cross product of any vector with itself is also equal to the 0 vector. We will formally prove these properties in a much later video. When vector A and vector B are parallel, the magnitude of the cross product will be 0. In this case, it will be a minimum. When vector A and vector B are perpendicular, the magnitude of the cross product will be a maximum. When theta is an acute or obtuse angle, the magnitude of the cross product between vector A and vector B will be a fractional portion or percentage of the maximum magnitude. Now let's talk about the direction of the vector produced by the cross product. There are always two directions perpendicular to a given plane, one on each side of the plane. How do we determine on which side will the vector produced from the cross product point towards? By convention, we use the right-hand rule. If we are trying to find vector A crossed with vector B, we can determine the direction of the new vector by pointing your right-hand fingers in the same direction as vector A, and then curl your fingers towards vector B. When curling your fingers, make sure you choose the smaller of the two possible angles, since theta was defined to be an angle between 0 and 180 degrees. Once you curl your fingers in the direction of rotation, your straight thumb will then point in the direction of the vector produced when you cross vector A and vector B with one another. A second way to think about the right-hand rule is by using three fingers: your thumb, index, and middle finger. The index and middle finger will represent the vectors that are being crossed with one another. These are the vectors that are located on the same plane. Your index finger will point in the direction of the first vector, in this case, vector A, and your middle finger will point in the direction of the second vector, in this case, vector B. Once you have aligned those fingers with the corresponding vectors, your thumb will point in the direction of vector A crossed with vector B. Now, on the other hand, if we are asked to find the cross product between vector B and vector A, we would obtain a totally different vector. In this case, we need to point our fingers in the direction of vector B and curl them towards vector A. Again, making sure you choose the smaller of the two angles. You will discover that your thumb now points in the opposite direction. The result is a vector that points in the opposite direction to the cross product of vector A and vector B. This also tells us that the cross product is not commutative. Vector A crossed with vector B is not the same as vector B crossed with vector A. In fact, they have equal lengths, but opposite directions. So keep this in mind when dealing with the cross product. We can also illustrate the geometric interpretation of the magnitude of the cross product. If the magnitude of vector A and vector B are represented by directed line segments with the same initial point, then the vectors form adjacent sides of a parallelogram, with base equal to the magnitude of vector A and altitude equal to the magnitude of vector B times sine of theta. Recall that the area of a parallelogram is given by the product of the base times the altitude. Thus, the length or magnitude of the cross product of vector A with vector B is equal to the area of the parallelogram determined by vector A and vector B. Lastly, let's compare both the dot product and cross product side by side. Many students get these vector operations mixed up since both involve multiplication of vectors. The first thing to remember is that both are operations involving multiplication of vectors. The difference is that the dot product will produce a scalar, and the cross product will produce a vector. In addition, the dot product is defined for vectors in R squared and R cubed. And the cross product is defined only for vectors in R cubed. The geometric definition of the dot product uses the cosine of the angle between both vectors, and the magnitude of the cross product uses the sine of theta between both vectors. And since the cross product also produces a vector, it will have a direction that is normal to the common plane between the two crossed vectors. If n hat represents a unit vector normal to the plane containing the cross vectors, then the cross product can be represented as follows. Alright, in our next video, we will go over the component definition of the cross product. The cross product, level 2. In the previous video, we covered the geometric definition of the cross product. In this video, we will derive another method to compute the cross product between two vectors in space by using their components. We can calculate the cross product A cross B directly if we know the x, y, and z components of vector A and vector B. We can calculate the components of the cross product using a procedure similar to that for the dot product. Let's first determine the cross products of the unit vectors I hat, j hat, and k hat. This will be pretty straightforward since the unit vectors I hat, j hat, and k hat all have a magnitude equal to 1, and they are perpendicular to each other. Recall from the previous video that the cross product between two vectors in space can be found by taking the product of the magnitudes of each vector times sine of the angle between the vectors. Let's use the geometric definition to find the cross product of all the possible combinations between the unit vectors, which include I hat cross I hat, j hat cross j hat, k hat cross k hat, I hat cross j hat cross k hat, and k hat cross I hat. The vector product of any vector with itself is equal to the zero vector. So I hat cross I hat, j hat cross j hat, and k hat cross k hat will all be equal to the zero vector. Next, let's find the cross product between I hat and j hat. Since the cross product between two vectors in space produces a vector that is orthogonal to these two vectors, it follows that the cross product is equal to k hat, since this unit vector is orthogonal to I hat and j hat, and it is consistent with the right-hand rule. In a similar fashion, j hat cross k hat is equal to I hat, and k hat cross I hat is equal to j hat. The following diagram is extremely useful for remembering the cross products between the unit vectors. For example, I hat cross j hat is equal to k hat. When moving along the arrows clockwise, the cross product is positive. And when moving along the arrows counterclockwise, the cross product will be negative. Next, we express vector A and vector B in terms of their components and the corresponding unit vectors. Then we go ahead and find vector A cross with vector B. We will find this by distributing the components. We then rewrite the individual terms as follows. Next, we go ahead and compute the cross products of all 9 terms. 3 of the terms will be equal to the zero vector, since these involve a unit vector crossed with itself. The remaining 6 terms will be equal to a unit vector, or the negative of a unit vector, depending on the order in which the unit vectors are crossed. The last step is to group the terms that contain the unit vector I hat, j hat, and k hat together. Doing that, we obtain the components of the final vector, which represents the cross product between vector A and vector B. Notice that the cross product produces a vector with an x, y, and z component. Recall that the dot product produces a scalar and not a vector. This is an alternative way of computing the cross product by using the components of two vectors in space. Similar to the dot product, we now have 2 distinct ways of computing the cross product. We can use the geometric definition or the component definition. The component definition of the cross product is not an easy formula to remember. Luckily, there is a handy mnemonic that you can use to remember the cross product. In order to make the component definition of the cross product easier to remember, we use the notation of determinants. If you're familiar with determinants from your previous math courses, you can go ahead and skip this section and jump straight into the determinant form of the cross product. We will first review the determinant of a matrix. Recall that the determinant of a square matrix, one that has equal number of rows and columns, is denoted by enclosing the entries of a square matrix with vertical lines as follows. For a 2x2 matrix, the determinant is defined by the following expression. Notice that we multiply the diagonals of the square matrix and subtract the results. In the end, we obtain a numerical value, and this numerical value is the determinant of the square matrix. This is also known as the determinant of order 2. For example, the determinant of the following matrices can be found by first multiplying the diagonal entries that move down from left to right and subtract the product of the entries that move downward from right to left. Notice that the determinant can be positive, negative, or 0. Now, to find the determinant of a 3x3 matrix, or a determinant of order 3, we need to break apart the 3x3 square matrix into 3 separate 2x2 square matrices. This can be accomplished by using the method of cofactors or cofactor expansion. We first need to find 3 minors of the 3x3 matrix. Recall that a minor is the determinant of the square matrix formed by deleting one row and one column from some larger square matrix. Since there are lots of rows and columns in the original matrix, you can make lots of minors from it. For our purpose, we will expand along the entries of the first row of a 3x3 square matrix. But you are free to choose which row or column you want to expand from. So given the following 3x3 square matrix with the given entries, we go ahead and find the 3 minors by first generating 3 2x2 square matrices by blocking the first row and systematically blocking each of the 3 columns. By blocking row 1 and column 1, we obtain the following 2x2 square matrix. By blocking row 1 and column 2, we obtain the following 2x2 square matrix. And finally, by blocking row 1 and column 3, we obtain the final 2x2 square matrix. Now that we have 3 2x2 square matrices, we find the minors by computing the determinant of each 2x2 square matrix. We are not done yet. Remember the row that we used to expand from? We will need to make sure that we multiply each of the entries of this row with its respective minor, as follows. Lastly, we need to determine the sign of the cofactor by using the following expression. Here, I and j represent the row and column number, respectively. For example, for the first cofactor, we use the entry located at row 1 and column 1, so the overall sign is positive. For the second cofactor, we use the entry located at row 1, column 2, making the overall sign negative. And for the third cofactor, we use the entry located at row 1 and column 3, making the overall sign positive. Do not worry about memorizing how one obtains the sign of the cofactor. It will always be positive, negative, and positive, as long as you're expanding from the first row, which for our purpose, it will always be the case. In the end, a determinant of order 3 can be found by using the following expression. For example, the determinant of the following 3x3 square matrix can be found as follows. We first find our 3 minors via cofactor expansion of the first row. Doing that, we obtain the following 2x2 matrices. Then, it is just a matter of finding the determinant of each 2x2 matrix and multiply this value with its respective entry from the first row as follows. Making sure we include the alternating sign positive, negative, and positive. Simplifying the expression, we obtain the following for the determinant of the 3x3 matrix. If we now rewrite the determinant of order 3 by replacing the first row with the standard unit vectors I hat, j hat, and k hat, and replace the second row with the components of vector A, and replace the third row with the components of vector B, then vector A crossed with vector B will be equal to the following determinant. Note the minus sign in the j hat component. The final expression for the cross product can be obtained by computing the determinant for each 2x2 square matrix, with each 2x2 square matrix representing a component of the cross product. Keep in mind that this 3x3 determinant form is used simply as an aid to remember the formula for the cross product. It is technically not a determinant because the entries of the corresponding matrix are not all real numbers, since we have the unit vectors in the first row. This is probably the easiest way of remembering and computing the cross product. A second method of computing the cross product does exist, and it is slightly easier, but many textbooks don't go over this method because it will only work for 3x3 determinants. This method modifies the determinant form of the cross product by copying the first two columns onto the end as follows. We now have 3 diagonals that move downward from left to right, and 3 diagonals that move downward from right to left. We essentially need to multiply along each of the 6 diagonals and add the product of the diagonals that move downward from left to right and subtract the product of the diagonals that move downward from right to left. In the end, you simplify by grouping the terms that contain the same unit vector. Notice that the j-hat component of the cross product is written with the negative sign distributed. Lastly, let's compare the component definition of the dot product with the component definition of the cross product. Many students get both of these vector operations confused. Notice that the dot product is found by multiplying corresponding components and adding them together, which results in a scalar quantity, while the cross product is found by carrying out operations with different components, which results in a vector. Alright, in our next video, we will go over a couple of examples and illustrate how to find the cross product between two vectors in space. The cross product, level 3. In this video, we will go over various examples illustrating how to find the cross product of two vectors in space by using both the geometric and component definition of the cross product. Let's jump straight into the first example. Find the magnitude of vector A crossed with vector B and determine whether A cross B is directed into the page or out of the page. Here, we're given two vectors that are located on a common plane. We're given the magnitude of both vectors and the angle between them. We can find the magnitude of the cross product by using the geometric definition of the cross product. So we go ahead and substitute the magnitude of the angle between the vectors into the formula. Computing the product of the magnitudes and sine of 60 degrees, we obtain the following. Simplifying the expression, we obtain 25 times the square root of 3 for the magnitude of the cross product. Now, to determine the direction of the cross product, we can go ahead and use the right-hand rule. Recall that this vector is going to be perpendicular to vector A and vector B, as well as a common plane containing these two vectors. Using the right-hand rule, we place our fingers in the direction of vector A so that our palm faces vector B and curl them towards vector B. In this case, our thumb will be pointing into the page, so we denote this vector with an X. If the vector pointed out of the page, then we denote the vector with a dot. Alright, let's try the next example. Find the magnitude of vector B crossed with vector A and determine whether B cross A is directed into the page or out of the page. Similar to the previous example, we are asked to find the magnitude of vector B crossed with vector A. We are given the magnitude of each vector and an angle. Notice that this angle is not the angle we usually use for computing the magnitude of the cross product by using the geometric definition, since this angle is not between vector B and vector A. We can easily find the angle between the two vectors by shifting vector A so that its tail aligns with the tail of vector B, as follows. Then, it is just a matter of using geometry to find the angle between vector A and vector B. In this case, it will be equal to 30 degrees. Now we can go ahead and find the magnitude of the cross product by using the geometric definition. Substituting the magnitudes and the angle between the vectors, we obtain the following. Simplifying the expression, we obtain 24 as the magnitude of the cross product. Next, we use the right-hand rule to determine the direction of vector B crossed with vector A. So we point our fingers in the direction of vector B with our palms facing vector A and curl them towards vector A. In this case, our thumb will point out of the page, so we use a dot to represent this vector. Alright, let's try the next example. The figure below shows vector v in the xy plane and vector u in the direction of positive k hat. Their lengths are 4 and 5 respectively. Find the magnitude of vector v crossed with vector u and determine whether the components of vector v crossed with vector u are positive, negative, or 0. Alright, here we have a diagram of vector v and vector u. We are first asked to find the magnitude of vector v crossed with vector u. We're given the magnitude of each vector. Note that the angle between the vectors can be obtained from the figure. We know that vector v is located on the xy plane, and vector u has only one component since it is pointing in the positive k hat direction. This means that vector v and vector u are orthogonal to one another, so the angle between these two vectors is 90 degrees, or pi over 2. Next, we go ahead and substitute these values into the geometric definition of the cross product. Simplifying the expression, we obtain 20 for the magnitude of vector v crossed with vector u. Next, let's use the right-hand rule to determine the direction of vector v crossed with vector u. We point our fingers in the direction of vector v, with our palms facing vector u, and curl our fingers towards vector u. Once again, our thumb will point in the direction of vector v crossed with vector u. In this case, it will have an x component that is positive, a y component that is negative, and since it lies on the xy plane, it will have a z component that is equal to 0. Let's try the next example. Find the cross product between vector A and vector B, and verify that it is orthogonal to both vector A and vector B. Alright, here we're given vector A and vector B in component form. We are asked to find the cross product between these two vectors, specifically vector A crossed with vector B. Let's go ahead and use the component definition of the cross product. We first need to set up our 3x3 determinant by using the standard unit vectors as the entries on the first row, followed by the components of vector A in the second row, and the components of vector B in the third row, as follows. Next, we go ahead and compute the determinant by cofactor expansion. So we first cover row 1 and column 1 and use the minor of the 2x2 matrix. This value will represent the x, or I hat component. Next, we write a negative sign and then cover row 1 and column 2 and use the minor of the 2x2 matrix. This value will represent the y, or j hat component. And finally, we cover row 1 and column 3. The minor of the 2x2 matrix will represent the z, or k hat component. Make sure you do not forget the negative sign in the y, or j hat component. This is a common mistake that many students make. Next, we go ahead and find the determinants of the 2x2 matrices. Then, we simplify each component, obtaining the following components for the cross product. The last thing we need to do is to show that this vector is orthogonal to both vector A and vector B. The easiest way to show this is by taking the dot product of this vector with vector A and vector B. The result should equal 0 if the vectors are orthogonal to one another. Computing the dot product with vector A gives us 0 as our answer. In the same manner, computing the dot product with vector B also gives us 0 as our answer. Hence, the vector produced by crossing vector A and vector B is orthogonal to both vector A and vector B. Let's move along to the next example. Find the cross product between vector A and vector B and verify that it is orthogonal to both vector A and vector B. Here, we're given vector A and vector B, written in standard unit vector form. Let's go ahead and rewrite the vectors in component form. Notice that vector B does not have a value for I hat, so the x component will be equal to 0. Next, we go ahead and set up our determinant. The first row will contain the unit standard vectors. The second row will contain the components of vector A, and the third row will contain the components of vector B. Then, we go ahead and find the minors by eliminating the first row in each of the 3 columns. Doing that, we obtain the following 2x2 determinants. Do not forget to include a negative sign in the j-hat component. Finding the determinant of each 2x2 matrix and simplifying, we obtain the following vector for the cross product between vector A and vector B. We can verify that this vector is orthogonal to both vector A and vector B by computing the dot product between these vectors. Using the component definition of the dot product, we obtain 0 for both vector A and vector B. Hence, vector A cross B is orthogonal to both vector A and vector B. Alright, in our next video, we will go over more challenging examples. The cross product, level 4. In this video, we're going to go over slightly more challenging examples that make use of both the geometric and component definition of the cross product. Let's go over the first example. Let u, v, w, and x be vectors in space. Which of the following expressions are meaningful? Which are meaningless? Explain your answer. Alright, for this problem, vector u, v, w, and x are all vectors in space. Recall that the dot product is defined for both vectors in r² and r³, while the cross product is defined for vectors in r³ only. Also, keep in mind that the dot product produces a scalar, and the cross product produces a vector. Let's use these facts and determine if the given expression is meaningful. Taking a look at the expression inside the parentheses, we see that we are taking the cross product between 2 vectors. This operation will produce a vector which will then be dotted with vector v, producing a scalar in the process. So this expression is meaningful. Let's take a look at the next expression. Here, the expression inside the parentheses is a dot product between 2 vectors, which reduces to a scalar. This scalar is then crossed with a vector. In this case, this expression is meaningless, because the cross product is defined only between 2 vectors. Let's take a look at the next expression. The operation inside the parentheses is a cross product between 2 vectors, which produces a vector. This vector is then crossed with another vector, which will produce yet another vector. So this expression is meaningful. Let's move along to the next example. The first expression in the parentheses is a dot product between 2 vectors, so this will reduce to a scalar. The expression in the second parentheses is also a dot product between 2 vectors, and it will also reduce to a scalar. In the end, we have a cross product between 2 scalars, which is not defined, so the entire expression is meaningless. Let's take a look at the next expression. Here, the expression in the first parentheses is a cross product between two vectors, so it will reduce to a vector. The expression in the second parenthesis is also a cross product between two vectors, so it will also reduce to a vector. In the end, we have the dot product between two vectors, which reduces to a scalar. So this expression is meaningful. Alright, let's move along to a different type of problem. Find the cross product between vector A and vector B, and verify that it is orthogonal to both vector A and vector B. Notice that this problem is slightly different when compared to the examples from the previous video, since vector A and vector B both have functions in their components. This seems like a much harder problem, but the way you calculate the cross product is exactly the same. You just need to make sure that you apply the properties of exponents along the way. Let's start by setting up our determinant. Next, let's go ahead and find the minor for each component. Then, we go ahead and compute the determinant for each 2x2 square matrix, making sure we correctly use the properties of exponents when multiplying the natural exponential functions. Simplifying the expression for each component, we obtain the following vector for the cross product. Next, let's find the dot product of this vector with vector A and vector B. Simplifying the dot product, we obtain 0 for both vectors. Hence, vector A crossed with vector B is orthogonal to both vector A and vector B. Alright, let's try the next example. Find two unit vectors orthogonal to both vector A and vector B. Alright, the quickest way to find a vector that is orthogonal to both vector A and vector B is by taking the cross product between these two vectors. The result will create a third vector that can be easily normalized to obtain the required unit vector. We can then multiply the unit vector by -1 to obtain the second unit vector. So let's start by finding the cross product between vector A and vector B. Since we are given the components of each vector, let's go ahead and use the component definition of the cross product and set up our determinant. Once we have our determinant, we go ahead and find the minors of the matrix. Then, we go ahead and compute each of the 2x2 determinants. Simplifying the expression, we obtain the following components for the cross product between vector A and vector B. Next, we go ahead and normalize this vector by dividing the vector by its magnitude. Computing the magnitude of this vector, we obtain the following. Then, it is just a matter of simplifying the components of each unit vector. The first vector will have the following components. And for the second vector, we simply multiply it by -1, obtaining the following unit vector. So these two unit vectors will be orthogonal to both vector A and vector B. Let's end the video with the final example. Find a vector v that is orthogonal to the plane that contains the points P, Q, and R. Here we're asked to find a vector that is orthogonal to the plane that contains 3 points. Recall that a plane is uniquely determined by 3 non-collinear points, points that are not all on a single line. In this problem, we're given the coordinates of 3 such points. In order to find a vector orthogonal to this plane, we need 2 vectors that are located on this plane, and compute the cross product with them. So our first task is to find 2 vectors that are located on this plane. We can easily do this by using the given points. Let's find the components of the vector formed by points P and Q first. So we subtract the coordinates of the points and simplify the expression, obtaining the following components for vector PQ. Next, let's find the components of vector PR. So we subtract the coordinates of the points with one another. Then, we simplify the expression, obtaining the following for the components of vector PR. Now that we have our two vectors, it is just a matter of taking the cross product between them. So we use the component definition of the cross product and set up our determinant. Then we find the minor for each component as follows. From here, we find the determinant of each 2x2 matrix. Lastly, we simplify each component, obtaining a vector with components equal to 8, 4, and 4. Note that any non-zero scalar multiple of this vector will also be orthogonal to the plane. This vector is going to be orthogonal to both vector PQ and vector PR, as well as a common plane between these two vectors. Finding a vector orthogonal to a plane is going to be extremely useful in this course, so it is important that you understand this example before you proceed. Alright, in our next video, we will switch gears and start covering and proving the algebraic properties of the cross product. The cross product, level 5. In this video, we will go over and prove various algebraic properties of the cross product. Let's start with the first algebraic property. Let U, V, and W be vectors in space, and let C be a scalar. Then, vector U crossed with vector V is equal to the negative of vector V crossed with vector U. In other words, the cross product is anti-commutative. This property tells us that both vectors have the same length, but opposite directions. This and subsequent properties can be proved by writing the vectors in terms of their components and using the component definition of the cross product. So we will let vector U be equal to the following components, and let vector V be equal to the following components. Then, by using the component definition of the cross product, we go ahead and set up our determinant and find the minors of the matrix. We then find an expression for the determinant of each 2x2 matrix. Simplifying the expression, we obtain the following for the cross product between vector U and vector V. Next, we do the same and use the component definition of the cross product to find vector V crossed with vector U. Doing that, we obtain the following expression for the components of vector V crossed with vector U. Taking a look at the two vectors, we see that the expression on the right can be obtained by multiplying the expression on the left by the scalar -1, as follows. And this ends the proof. Let's take a look at the next property. Vector U crossed with the sum of vector V and vector W is equal to vector U crossed with vector V plus vector U crossed with vector W. In other words, the cross product is distributive over addition. To prove this property, we write vector U, V, and W in component form, and find an expression for the components for both the left and right-hand side of the expression. Let's start with the left-hand side. We first add vector V with vector W. Doing that, we obtain the following components. Then, we go ahead and find the cross product between vector U and the sum of vector V and vector W. Doing that, we obtain the following components. Next, we go ahead and distribute the components of vector U, obtaining the following. Now we go ahead and do the same for the right-hand side of the expression. So we first find vector U crossed with vector V, obtaining the following expression. Then we find vector U crossed with vector W, obtaining the following expression. We go ahead and add these two vectors together and compare it to the left-hand side. Notice that every single component on the right side matches with its corresponding component on the left-hand side. Thus, both sides are equivalent, and this ends the proof. Let's take a look at the third property. scalar c times vector u crossed with vector v is equal to scalar c times vector u crossed with vector v, which is also equal to vector u crossed with scalar c times vector v. When multiplying by a scalar, you are free to multiply any of the two vectors and proceed with the cross product. Let's move along to the next property. Vector u crossed with the 0 vector is equal to the 0 vector crossed with vector u, which is equal to the 0 vector. So a vector crossed with a 0 vector is essentially equal to the 0 vector. The fifth property is vector u crossed with itself is also equal to the 0 vector. We can easily prove this by representing vector u in component form and finding the cross product. Notice that the value of each component reduces to 0. Recall that this is the definition of the 0 vector, and this ends the proof. The sixth property is vector u dotted with the cross product of vector v with vector w is equal to the cross product between vector u and vector v dotted with vector w. In other words, this represents an exchange of dot and cross product. The expression on the left-hand side of this property is also known as a scalar triple product, or triple scalar product. We will talk about this property in more detail in a later video. The proof of this property is very similar to the previous proofs. We go ahead and denote each vector in component form. Then we work with the left-hand side and find an expression in terms of these components, and do the same for the right side of the expression. In the end, both the left and right side should have identical expressions for their components. So let's start with the left-hand side and find the cross product between vector v and vector w. We then take this vector and dot it with vector u. Then we go ahead and distribute the components of vector u as follows. Next, we work with the right-hand side and find the cross product between vector u and vector v, obtaining the following vector. Then we dot this vector with vector w, obtaining the following expression, making sure we also distribute the components of vector w. Notice that each of the terms on the right side can be found on the left side of the expression. So this property has been verified. And this ends the proof. The last property is vector u crossed with the cross product between vector v and vector w is equal to the dot product of vector u with vector w times vector v minus the dot product between vector u and vector v times vector w. The expression on the left-hand side of this property is also known as the vector triple product, or triple vector product. Alright, and these are the 6 algebraic properties of the cross product that you should be familiar with. They will be very useful when solving various types of problems and when you need to derive certain expressions in the fields of mathematics and science. Alright, let's go over a couple examples that make use of these algebraic properties. Given vector A and vector B, find vector A crossed with vector B and vector B crossed with vector A. Alright, we're given vector A and vector B in component form, and we are asked to find 2 separate cross products. Let's use the component definition of the cross product. So let's set up our 3x3 determinant and find the minor for each component. Next, let's compute the determinant of each 2x2 matrix. And then we simplify, obtaining the following vectors for each cross product. Notice that the cross product is not commutative and is order sensitive. In fact, it is anti-commutative. Recall that this was one of the algebraic properties of the cross product. Alright, let's try the next example. Given vector A, vector B, and vector C, show that vector A crossed with the cross product between vector B and vector C is not equal to the cross product between vector A and vector B crossed with vector C. The simplest way to show that both operations are not equal is by simply computing the left and right-hand side and directly compare the results of both operations. Let's start by computing the left side first. So we first find an expression for vector B crossed with vector C. Then we take vector A and cross it with this vector. Doing that, we obtain the following vector. Next, we do the same for the right-hand side. So we first find vector A crossed with vector B. Doing that, we obtain the following vector. Next, we take this vector and cross it with vector C, obtaining the following vector. Taking a look at both vectors, we see that they are not equal to one another. This example illustrates that the cross product is not associative. Alright, let's go over the next example. Verify Lagrange's identity if vector A and vector B are in R cubed. Alright, we will let theta be the angle formed between vector A and vector B. Then, the dot product on the right side of the identity can be written as the magnitude of vector A times the magnitude of vector B times cosine of theta. This is essentially the geometric definition of the dot product. Next, we use the property of exponents to rewrite this expression as follows. Then, we can go ahead and factor out the common factor as follows. We can now use a Pythagorean identity and replace the 1 minus cosine of theta squared term with sine of theta squared. Doing that, we obtain the following. Notice that this expression is nothing more than the magnitude of the cross product between vector A and vector B squared. And this ends the proof. This identity will be useful to prove the geometric property of the cross product in the next video. Alright, let's go over the final example. Prove vector A minus vector B crossed with vector A plus vector B is equal to 2 times vector A crossed with vector B. Alright, let's work with the left side of the expression. We will first apply the distributive property for cross products and expand the left side of the expression as follows. Making sure we do not change the order of the cross products, since the cross product is not commutative. Here, vector A crossed with vector A and vector B crossed with vector B reduces to the 0 vector. The last two cross products are related to one another since one expression is just the negative with the order of the vectors reversed. Replacing this second expression, we obtain the following. Simplifying the expression, we obtain 2 times vector A crossed with vector B. And this ends the proof. Alright, in our next video, we will go over the geometric properties of the cross product. The cross product, level 6. In this video, we will focus on the geometric properties of the cross product between two vectors in space. Let's start with the first geometric property. Let vector u and vector v be non-zero vectors in space, and let theta be the angle between vector u and vector v. Then, vector u crossed with vector v is orthogonal to both vector u and vector v. This property was illustrated in the first video of this series. Now we want to formally prove this geometric property. In order to show that vector u crossed with vector v is orthogonal to vector u and vector v, we will make use of the dot product. If both vectors are orthogonal to one another, then the dot product should equal 0. So we first denote the vectors in component form. as follows. Now we go ahead and find the cross product between vector u and vector v. Doing that, we obtain the following vector. Next, we go ahead and dot this vector with vector u and vector v separately. Then, we go ahead and distribute the components of vector u and vector v for each expression. From here, notice that every single value cancels out, reducing both expressions to 0. Therefore, vector u crossed with vector v is orthogonal to both vector u and vector v. And this ends the proof. Let's move along to the next geometric property. This property was also introduced in the first video of this series. Recall that we used the right-hand rule to determine the direction of the vector produced from the cross product of two vectors. This property is used to calculate the length or magnitude of the vector produced when crossing two vectors. So the magnitude of the cross product between vector u and vector v is equal to the magnitude of vector u times the magnitude of vector v times sine of theta. Recall that theta is an angle between 0 and pi. We can prove this property by starting with the component definition of the cross product and finding an expression for the magnitude of the cross product. We are going to work with the square of the magnitude. So this expression will simplify to the following expression. Let's go ahead and expand each of the terms as follows. Next, we notice that the magnitude of vector u times the magnitude of vector v squared can be represented by using the components of the vectors as follows. Distributing the quantities, we obtain the following expression. In a similar fashion, the dot product between vector u and vector v squared is written as follows. Expanding the expression, we obtain the following. Notice that if we take the expression that represents the product of the magnitude squared and subtract it from the expression representing the dot product squared, we obtain the same expression for the magnitude of the cross product squared. So this long expression can be written as the difference between these two quantities. This expression is referred to as Lagrange's identity, which was introduced in the previous video. Now that we have rewritten the right-hand side using these expressions, let's go ahead and use the geometric definition of the dot product and write vector u dotted with vector v as the magnitude of vector u times the magnitude of vector v times cosine of theta. Then, we use the property of exponents to rewrite this expression. Next, we factor out the product of the magnitudes squared. From here, we replace 1 minus cosine of theta squared with sine of theta squared by making use of the Pythagorean identity sine squared plus cosine squared equals 1. The last step is to take the square root of both sides. And since theta is an angle between 0 and pi, the square root of sine of theta will always be positive. And this ends the proof. The third geometric property is vector u crossed with vector v is equal to the 0 vector if and only if vector u and vector v are scalar multiples of each other. In other words, two non-zero vectors u and v are parallel if and only if vector u crossed with vector v is equal to the 0 vector. We can prove this by noticing that if vector u is a scalar multiple of vector v, then vector u can be replaced with scalar c times vector v. Then we apply an algebraic property of the cross product, which rewrites the expression to scalar c times the cross product of vector v with itself. Recall that a vector crossed with itself is just equal to the 0 vector. So this entire expression simplifies to the 0 vector. Alternatively, vector u and vector v are parallel if and only if theta equals 0 or pi. since sine of theta at these angles reduces to 0, and therefore the magnitude of vector u crossed with vector v reduces to the 0 vector. And this ends the proof. The final geometric property was also introduced in the first video of this series. The magnitude of vector u crossed with vector v is equal to the area of a parallelogram having vector u and vector v as adjacent sides. To prove this property, we can use a parallelogram with vector u and vector v as adjacent sides. We can find an expression for the area of the parallelogram, given the magnitude of vector u and vector v, as well as the angle between both vectors. In this case, the base of the parallelogram will be equal to the magnitude of vector u, and the altitude of the parallelogram will be equal to the magnitude of vector v times sine of theta. This expression is nothing more than the magnitude of vector u crossed with vector v. And this ends the proof. Now let's go over a couple of examples that make use of the geometric properties of the cross product. Show that the quadrilateral with vertices A, B, C, and D is a parallelogram, and find its area. Determine if the parallelogram is a rectangle. Okay, here we are given the coordinates of 4 distinct points. We need to show that these points form a parallelogram. We do this by showing that both pairs of opposite sides are parallel. Let's go ahead and find the vector representation of each side. Vector AB, AD, CD, and CB will have the following values for their components. Notice that vector AB is equal to the negative of vector CD, and vector AD is equal to the negative of vector CB. This means that vector AB is parallel to vector CD, and vector AD is parallel to vector CB, since the vectors are a constant multiple of one another. Now that we have shown that the vertices form a parallelogram, we go ahead and find the area by finding the magnitude of the cross product between two adjacent vectors. Let's first find the cross product between vector AB and vector AD. Setting up the determinant and finding the minors, we obtain the following. Simplifying the expression, we obtain the following components for the cross product. Next, we go ahead and find the magnitude of this vector. Doing that, we obtain the following for the area of the parallelogram. Lastly, we can quickly check to see if the parallelogram is a rectangle by computing the dot product between the same vectors. If the dot product is equal to 0, then the vectors are orthogonal and therefore represent the sides of a rectangle. Computing the dot product, we obtain -2. Since the dot product is not equal to 0, this parallelogram is not a rectangle. Alright, let's try the final example. Find the area of a triangle that contains the points P, Q, and R. This problem looks very familiar. The points in this problem are exactly the same from an example in the previous video. In this case, we are now asked to find the area of the triangle as opposed to a vector that is orthogonal to the plane. We can find the area by making use of the geometric definition of the cross product. So let's first find the area of a parallelogram by crossing two adjacent vectors. We will then divide that area in half to obtain the area of the triangle. Let's find the component form of vector PQ and vector PR. Then we go ahead and cross these two vectors with one another. Simplifying the expression, we obtain the following components. Next, it is just a matter of finding the magnitude of this vector. Computing the magnitude and simplifying, we obtain the following value. Since this value represents the area of a parallelogram, we need to divide this value in half to obtain the area of the triangle. Doing that, we obtain the final answer equal to 2 times the square root of 6. Alright, in our next video, we will go over our first applications that make use of the cross product. The cross product, level 7. In this video, we will go over our first application of the cross product. In the previous video, we used the cross product to find the area of a parallelogram formed by 2 adjacent vectors. We can extend this idea to 3-dimensional space and use the cross product to determine the volume of a parallelepiped, a polyhedron whose faces are all parallelograms. If vector A, vector B, and vector C are an arc cubed, then vector A dotted with the cross product of vector B and vector C is called the scalar triple product, or triple scalar product. The scalar triple product can be written in determinant form by using the components of the vectors as follows. Note that the value of the determinant is multiplied by -1 if 2 rows are interchanged. After 2 such interchanges, the value of the determinant will be unchanged. So, the following triple scalar products are also equivalent. If vectors A, B, and C do not lie in the same plane, the triple scalar product can be used to determine the volume of the parallelepiped, with vector A, B, and C as adjacent edges. In this figure, the area of the base is a parallelogram and can be found by computing the magnitude of the cross product between vector B and vector C. If we were to draw the vector obtained by crossing vector B and vector C, we obtain a vector that is orthogonal to the plane containing these 2 vectors. Now, if we use theta to represent the angle between vector A and the cross product between vector B and vector C, then the height h of the parallelepiped will be equal to the magnitude of vector A times the absolute value of cosine of theta. Note that we must use the absolute value of cosine of theta instead of cosine of theta in the case when theta is greater than pi over 2, since we want the height to be a positive number. The volume of the parallelepiped is going to be equal to the area of the base times the height. Substituting these expressions for the area of the base and the height, we obtain the following expression for the volume of the parallelepiped. Recall that this is nothing more than the geometric definition of the dot product, making sure we take the absolute value since volumes are positive values. We can also use the scalar projection of vector A onto the vector produced by crossing vector B and vector C. Again, making sure we use the absolute value of the scalar projection since the height will be a positive number. The magnitude of the cross product cancels out, and we are left with the same expression for the volume of the parallelepiped. A natural consequence of the scalar triple product is that the volume of the parallelepiped is 0 if and only if all 3 vectors are coplanar. That is, if vector A, B, and C have the same initial point, then they will lie in the same plane if and only if the scalar triple product is equal to 0. The last thing to keep in mind is that the expression obtained by crossing vector A with the cross product of vector B and vector C is called the vector triple product, or triple vector product. This expression is very useful for simplifying vector calculations in physics. In this course, we will mainly use the scalar triple product and not the vector triple product. Alright, let's go over a couple of examples that make use of the scalar triple product. Find the volume of the parallelepiped whose edges are vectors A, B, and C. In this problem, we are given 3 vectors in component form. These vectors represent the edges of a parallelepiped. We can easily find the volume of the parallelepiped by computing the scalar triple product. So let's write the scalar triple product in determinant form as follows. Next, let's go ahead and find the minors by expanding row 1. We then find the determinant of each 2x2 matrix and simplify. Doing that, we obtain the final answer equal to 82 cubic units. Alright, let's go over the next example. Find the volume of the parallelepiped with vertices P, Q, R, and S, and vectors PQ, PR, and PS as adjacent edges. Alright, similar to the previous example, we are asked to find the volume of the parallelepiped. We are not given the components of the vectors, so we first need to find them. Subtracting the appropriate coordinates from one another, we obtain the following components for vector PQ, PR, and PS. Next, we go ahead and compute the scalar triple product. So we set up our determinant and find the minors as follows. Then we find the determinant of each 2x2 matrix and simplify the expression. Doing that, we obtain -3. Recall that the volume has to be a positive number, so we take the absolute value, obtaining 3 cubic units as the final answer. Let's try the next example. Use the scalar triple product to verify that vector A, B, and C are coplanar. Here we're given 3 vectors in standard unit vector form. Let's rewrite them in component form. We are asked to determine if the vectors are coplanar. We can easily determine this by calculating the scalar triple product, and if the result is equal to 0, then the vectors are coplanar. So let's set up our determinant as follows. Next, let's find the minors of the matrix. Then we compute the determinant of each 2x2 matrix. Simplifying the expression, we obtain 0 as our final answer. This means that the volume of the parallelepiped is equal to 0. This result confirms that all 3 vectors are coplanar. Alright, let's go over the final example. Use the scalar triple product to determine whether the points P, Q, R, and S lie in the same plane. Alright, this is very similar to the previous example. We are given the coordinates of 4 points instead of providing us with vectors. In order to determine if all 4 points are coplanar, we need to generate 3 vectors for which all have a common initial point, but have distinct terminal points. For this problem, I will use point P as a common point. This way, I can generate vector PQ, PR, and PS. We first need to find the component form of each vector. This can be done by subtracting the terminal point from the initial point for each vector. Doing that, we obtain the following components. Next, we need to calculate the scalar triple product, so we set up our determinant and find the minors. Doing that, we obtain the following. Computing the 2x2 determinants and simplifying, we obtain the final answer equal to 0. All 3 vectors are coplanar since the volume of the parallelepiped is equal to 0. Since these 3 vectors also include all 4 points, we can also conclude that points P, Q, R, and S also lie in the same plane, so they are coplanar. Alright, in our next video, we will go over our final application and learn about torque. the cross product, level 8. In this video, we will go over one final application of the cross product. In the fields of physics and engineering, a body can have both translational and rotational motion. Recall from a previous video that the net force applied to a body causes the body to accelerate at a particular direction. It turns out that a body can still experience motion even if the net force acting on the body is equal to 0. For example, say we have a box whose mass is uniformly distributed and is sitting on a table. If we apply two equal forces and opposite in direction along the center of the box, this will create a net force equal to 0, and the box will not accelerate. It will have no translational motion. On the other hand, if we shift these same forces so that they point away from the center of the box as follows, this will cause the box to move. Specifically, it will cause the box to rotate, even though the forces were equal in magnitude but opposite in direction. The application of these forces caused the box to rotate. This means that a body can have rotational as well as translational motion. If we assume that an object can be treated as a rigid body, a body in which forces that act on them do not cause deformations, such as stretching, twisting, and squeezing, then the tendency for an object to rotate about an axis due to the application of a force is referred to as the torque on the object. You can think of torque as a physical quantity that describes the rotational or turning effort of a force. Just like the net force acting on a body gives rise to a linear acceleration, the net torque on a rigid body gives rise to an angular acceleration. In physics, the cross product can be used to measure torque. This is also known as the moment m of a force F about a point P. Usually, physicists tend to use the word torque, while engineers usually use moment. In either case, it is important to specify about which point the force is acting on. It is not enough to just say, find the torque. Torque is always defined with reference to a specific point, so keep this little detail in mind. In the figure shown, a force F is applied at point Q. So the moment of the force F about point P is given by the following expression, vector PQ crossed with the force F. The magnitude of the moment m measures the tendency of vector PQ to rotate counterclockwise about an axis directed along vector m, which is perpendicular to both vector PQ and the force F. We can determine the way it will rotate by using the right-hand rule introduced in the previous videos. The concept of a moment makes more sense if we use a bolt and a wrench. We can tighten a bolt that is located at point P and is perpendicular to the XY plane. By applying a force on the wrench, this will produce a turning effect. In this case, we are producing a moment or a torque relative to point P, or in this case, the origin. If we use vector r to denote the position vector from point P to the point where the force F is being applied, in this case, point Q, then the torque about the origin, or point P, is represented by the Greek letter tau, and can be written alternatively as follows, vector r crossed with vector F. The vector produced from the cross product of these two vectors measures the tendency of the rigid body to rotate about the origin. The direction of the torque vector indicates the axis of rotation. So the bolt and the wrench will rotate about this axis. The magnitude of the torque vector can be found by using the geometric definition of the cross product. In this case, the magnitude of the torque about the origin will be equal to the magnitude of the position vector r times the magnitude of the force F times sine of the angle between the position and force vector. Notice that if the force is applied closer to the axis of rotation, the rigid body experiences less torque, even though the same force is being applied. If the angle between the position vector and force vector stays the same, we can generate a greater torque by simply applying the force further away from the axis of rotation. Also notice that the only component of the force vector F that can cause a body to rotate is the one perpendicular to the position vector r, or in this case, the magnitude of the force vector F times sine of theta. If the force vector points parallel or anti-parallel to the position vector r, this force will not cause the wrench to rotate, so it will not tighten or loosen the bolt. On the other hand, if the force is applied at an angle, then we break apart the force vector into components that are parallel and perpendicular to the position vector. In any case, it is the orthogonal component of the force that causes the wrench to rotate. The magnitude of the torque vector is essentially equal to the area of the parallelogram with the position vector r and force vector F as adjacent sides. By using the right-hand rule, we can determine if the wrench will be rotating clockwise or counterclockwise. If the wrench is rotating counterclockwise, then the torque vector will be pointing up out of the page or plane. If the wrench is rotating clockwise, then the torque vector will be pointing down or into the page or plane. By convention, we usually assign counterclockwise rotations to be positive torques, or have positive sense, and clockwise rotations are considered to be negative torques, those that have negative sense. This is the same conventions that we use when measuring angles in standard positions. We also use a dot to represent a vector that points out of the page or plane, and a cross to represent a vector that points into the page or plane. The SI unit of torque is the Newton meter. Now, this is going to be a little confusing because this was the same unit that we used for measuring work, which was introduced in the dot product video series. In the case of work, the unit was measuring energy in joules. Despite this, it is important to understand that torque is not work or energy. Torques should always be expressed in Newton meters and not joules. This will help avoid mistakes and misunderstandings. In the US customary system, the unit of force is the pound force, and the unit of distance is the foot. So the unit of torque is the foot-pound. Sometimes they pronounce this quantity as pound-foot to differentiate it from the units of work. Alright, these are the basics of torques. This topic is covered more extensively in a typical physics course. And for this multivariable calculus course, the concepts covered are more than enough to solve typical problems. In our next video, we will do just that and go over various torque examples. The cross product, Level 9. In this final video on the cross product series, we will go over various torque examples. Let's jump straight into the first example. A vertical force of 50 pounds is applied to the end of a 2-foot lever that is attached to an axle at point P and located on the YZ plane. Find the moment of this force about point P when theta equals 60 degrees. In this problem, we are asked to find the moment of the force F about point P when theta equals 60 degrees. Recall that moments and torques represent the same quantity. We can find the moment or torque in two distinct ways. We can use the component definition or the geometric definition of the cross product. Since the torque is defined as the cross product between the position vector r and the force vector F, let's go ahead and solve this problem by using the component definition. In order to use the component definition of the cross product, we need to find the components of the position vector r and the components of the force vector F. Since the force is directed vertically downward, the force vector will only have a z component of negative 50 pounds. The other components will be equal to 0. For the position vector, we can find the y and z components by using right triangle trigonometry. Notice that the position vector is located in the yz plane, so it will have a y component equal to 2 times cosine of 60 degrees, which is equal to 1. And the z component will be equal to 2 times sine of 60 degrees, which is equal to the square root of 3. Now that we have the components of both the position and force vector, let's go ahead and find the moment or torque about point P. We start by setting up our determinant as follows. Next, we go ahead and find the minors of the matrix. From here, it is just a matter of computing the determinant of each 2x2 matrix. Doing that, we obtain the following components for the moment. So the torque vector will point in the negative x direction and will have a magnitude equal to 50 foot-pounds. Note that the moment is dependent on the angle formed by the lever and the positive y-axis. When theta equals pi over 2 and the force stays constant, the moment is equal to 0, since the force will be pointing in the same direction as the position vector. The moment is greatest when the angle is equal to 0 degrees. In this configuration, the position vector and force vector will be orthogonal to one another. Alright, let's try the next example. Find the magnitude and direction of the torque about point P if a 36-pound force is applied as shown. Alright, here we have a rigid body in the shape of an L, and a force of 36 pounds is applied at an angle of depression of 30 degrees at one end. We need to find the magnitude and direction of the torque. Notice that in this problem, the rigid body and the force vector F are all located in the same plane. So the torque vector is going to be orthogonal to this plane. It will either point into the page or out of the page. We need to use the definition of torque in order to find both the magnitude and direction. Once again, we have two distinct ways to solve this problem. We can go ahead and find the components of the position vector r and the components of the force vector F, and use the component definition of the cross product by setting up a determinant. Or we can use the geometric definition and find the magnitude of the position vector r and force vector F and multiply these values by sine of the angle between these two vectors. Let's solve this problem by using the geometric definition. Let's first find the magnitude of the position vector. The position vector will start at point P and end at the point where the force is being applied. Since we are given the dimensions of the part, we can easily find the magnitude by using the Pythagorean theorem, since we have a 45-45-90 right triangle. Simplifying the expression, we obtain the following value for the magnitude of the position vector r. The magnitude of the force vector F was given to us, and it was equal to 36 pounds. All we need now is the angle between the position vector r and the force vector F. We can use basic geometry to find this angle, or if you decide to solve this problem by using the component definition of the cross product, you can use the dot product to find the angle between the position and force vector. Let's move the position vector forward so that its tail matches the tail of the force vector. Notice that we have vertical angles and complementary angles. By using geometry, the angle between the position vector and the force vector is going to be equal to 45 plus 60 degrees. So the angle between both vectors is 105 degrees. Next, it is just a matter of substituting all these values into the geometric definition of the cross product. Doing that, in approximating the value, we obtain 197 foot-pound for the magnitude of the torque. The direction of the torque can be determined by using the right-hand rule. The applied force will cause the shape to rotate clockwise, so the torque vector will be pointing into the board. So we use an X to show the direction of the torque vector. Alright, let's go over the final example. The specifications for a tractor state that the torque on a bolt with head size 7/8 inches cannot exceed 200 foot-pounds. Determine the maximum force that can be applied to the wrench in the figure. Alright, similar to the previous example, let's use the definition of torque and use it to find the maximum force one can apply to the bolt. Since we are given the magnitude of the position vector and we are also provided with various angles, we're going to use the geometric definition of the cross product to solve this problem. You're free to use the component definition as well. You just need to find an expression for the components of the position and force vector. This will require a little more work. Nevertheless, it is an acceptable way of solving the problem. Alright, notice that we are given the magnitude of the position vector and the magnitude of the torque. We are also given two separate angles. Notice that the 50-degree angle is irrelevant to the calculation of torque, since we are interested on the angle formed between the position and force vectors. In this case, the angle we need can be found by subtracting 70 degrees from 180 degrees. Now that we have our angle, let's go ahead and substitute these expressions into the geometric definition of the cross product. At this point, it is just a matter of solving for the magnitude of the force vector F. Doing that, in approximating our answer, we obtain 106.4 pounds as the final answer. Alright, and this ends the cross product video series. In our next series of videos, we will learn how to write and generate the equation of lines and planes.